our next session will be a research highlight given by our mission faculties, Dr. Kang from Department of Mechanical Engineering, Dr. Sauer, and Dr. Nirmal Ghimire from Department of Physics and stuff.
All right. So thank you for attending talks, and I'm going to just briefly give you the overview what I've been doing affiliated and quantum sensing. So my research, first of all, focuses on the 3D materials with the mechanics, and I'm affiliated. The main affiliation is the mechanical engineering. So I'm going to talk about how the mechanical engineers will contribute to the quantum sensing and material science and engineering, with focus on specifically on manufacturing of 3D materials. That's about so first, let me talk about the research focus here a little bit more detail. So I'm working on the 2D materials and how I can make structures like Dr. Cho just introduced, and that was my research when I was a postdoc. And then I move on to the Mason, and then right now I'm doing research with the 3-dimensional force graphing. I'm going to talk a little bit more detail in these slides. So I'm working in an area of biohealth, so with quantum sensing, main application with the biosensors. So before I talk about my research, let me just briefly give you an overview what I was doing. So my groups and in Quantum Science and Engineering Center, we have several groups that we are doing research with the different focuses. One of the groups is quantum sensing. So here, Dr. Pressmans and Venezianos and Chitzinis, they are doing research with nanomaterials. One of them in material they are interested in with a focus on the DNA origami. And here they are using the DNA origami here. So using the DNA origami to use as a probe to measure the action potential to study the epilepsy. So just to give you a brief ideas about the epilepsy is the neurological disorder and action potential move through the neurons, and to measure the abnormal signals, then we use our groups uses the DNA as a probe to measure the action potential here. So that's one of the kind of research, and I hope that this gives you a sense of what we are doing using the nanomaterials for quantum sensing. So moving on, my research focused on the nanomaterials for biomedical research applications. Exactly, as a proof that the shapes and morphology of their DNA modules will be different or differently behaved. So the signals that we are picking up from cells will be different. So how efficiently we measure the small amplitude of the signal flowing through the neurons, that's the deal. So for these applications for biohealth, people use different types of materials. Nanomaterials is one of the types. So I'm interested in the graphene material. People talk about the characteristics, exceptional characteristics of the graphene, the high mobility, electron mobility that allows the fast response for sensors, and what else? The high conductivity and mechanical flexibility for wearable sensors. So all that we benefit from those characteristics of the nanomaterial. So as a mechanical engineer, so one of the deal is that how we can make the 2D materials with the low cost to make the compact and small platform as a sensors, and also mass produce the materials with the low cost, and that's the deal. So I'm going to talk about how we can scalably produce the graphene material, and we can structure how we can make the structures in an atomic scale material. So using nanomaterials, we explore different types of fields here, plasmonics and all that. So we use the small scale structures to modulate the material property. Even as I mentioned, the graphene itself has exceptional property, but what we are working on to enhance those properties even with, the exceptional material property using nanomaterial, not structures. So how we can make small scale structures in a nano micro scale, that's what we do. And here's how we fabricate those graphene material. In our lab, we use the CVD technique. So CVD, chemical vapor deposition, we use the gas, methane. Methane is CH4, so we decompose C carbons and at very high temperature, 1,000 degrees Celsius. But it takes about 3 to 4 hours. Right? So we get about 5 by 5 centimeter scale, and then we transfer to the substrate, and then we make and fabricate the device. It takes a lot of effort to make the sensor. So the objective of our research is that how we can make those materials in a fast and manners and with a low cost. Right? That's the main purpose here. Just to give you a sense of how we can use these materials, we make the elements of the biosensors. For example, photodetectors, graphene is sensitive to light, so how we can make the device more sensitive to the light, and we use those nanostructures here, well, crumples and wrinkles, and that gives us a larger area, specific area. So we have more light to observe here. That's the main mechanism how we can make a device with enhanced performance here. With photodetectors, we make the structures and make the higher sensitivity to the light. And we use these types of materials to integrate in the wearable platform. For example, just to give you an idea how we integrate this device into the wearable sensor. So one of the characteristics to make the wearable sensors, those devices should be stretchable. Because remember, well, suppose that those devices on our skin, as we move, they are stretchy with about over 10%. Well, conventional material usually is sustain a few less than 1% of strain. So as we make these materials with the structures, we can make the material more stretchable and highly sensitive to any needs here. So we make this material. So we started to make and manufacture this material using lasers. So as I mentioned, that we use the CVD to fabricate the synthesize the graphene material. But now the mechanism is the same. As we shine the very strong light onto the polymer, so now we use the polymer as a precursor. So we use the methane to get the carbons. But here now we use the polymer here, the polymer, for example, and then we shine the light, and then they locally increase the temperature up to like over 1,000. That's the way we can fabricate the material in less than a second, in some order of microsecond actually. So this way we can fabricate the device directly without transferring the graphene onto the substrate to make the wearable and flexible material. To give you a sense, what we did, the hydrogen sensors. So here we combine the two different types of material, metal, nanoparticles, and graphene with our approach that we use the laser photothermally, that contains with the polymer thin film that contains the precursors, carbons and nanoparticles. Conventional methods use other methods like the solution processing, and that way, we can spread the nanoparticles onto the graphene, but the performance of the materials with the hybrid materials with solution processing is not greater than the one that we just made with our approach, because the electron transfer between the nanoparticles and graphene, as we improve the interface with the coherent structures between the two different types of material, then we can enhance the performance of the sensors here. So here, material is mechanically robust. So imagine that the nanoparticles are on top of the graphene, and as we bend it, then the nanoparticles will move around. But as we have a coherent structure, coherent material, what I mean by the coherent material is that the nanoparticles is embedded like a chocolate chip on the muffins. Then it might be robust and reliable even to the bending. So we make those types of sensors, and one of the applications is electrochemical sensors. So, and this has a potential for, well, the seal and lattice productions of the material, at the same time, direct application of those wearable and flexible sensors. So, with that, I'll just stop here, and I just, well, tell you that this is kind of research that we are doing with nanomaterials to, well, develop a wearable and flexible sensors based on the quantum sensing. So I hope that I gave you a sense that what we do and answer any questions.
One question could be one of you guys next time.
A quick question. So this whole propylene of graphene, there's many other materials you can make in layered forms. How much has been studied about what mechanical buckling and things does to their materials?
So in terms of the property, people talk about electrical, mechanical, and optical properties. And those, I mean, different field, electrical, and mechanical engineers, people have different interests. For example, as a mechanical engineer, we use the materials for flexible sensors. So we are interested in how we can make those materials more flexible, but at the same time, we are interested in how we can modulate the electrical property of the material with the spin. So, I mean, so we work with people in a different field. So,
I have a quick question. How much control do you have over the detection wavelengths for your photodetectors?
detection wavelengths. So that's really good question. So graphene, people consider it as a selective electron material. So it shows a broad band detection capabilities. So, yeah, all the way.
That's correct. But we can talk offline or sometime later. Next week. Thank you.
Hi, I'm Karen. Nice to see you. It's really loud in here. I realized when I was sitting in the back, like you guys are under like this constant. You got the Stranger Things going on there with the lights going on and off. Anyway, welcome, and I am talking about quantum magnetometers. And the basic idea is, can we use light and atoms to detect something as opposed to electrons and circuits? So the conventional technique is electrons and circuits, and we would like to use light and atoms. Okay, and although I'm giving the talk, in fact, the people who really made the slides is Robert Cooper, who's sitting right here, and Darwin Heroes, who's in the back. You can wave your hand. So they're the ones who did the real work. So the basic idea, before I get into any slides, is that atoms can be easily tuned through something known as Zeeman resonance. You put a magnetic field on them, there's a spin up and a spin down. You change the magnetic field, you change the energy splitting between them. You create the resonance frequency. So whatever you want to measure has a frequency, and you can tune the atoms just with a small magnetic field. And apply atoms, say for instance, if you put just a Gauss, which is just twice Earth's magnetic field, that's 0.7 megahertz. So you don't need a lot of field to get a nice resonance frequency. But one of the things that's great about atoms is the ease of resonance tuning. So I'll talk a little bit about using that to detect explosives. The other thing that I want to talk about is this idea of what's called common mode rejection. So imagine you're in a really noisy environment. You're looking for something small. And one way to do it is to measure the environment and measure your signal at the same time and then subtract them. That way you can get your small signal on top of your big background. The problem with electronics is that you measure both. And then if your signal is really much smaller than your background, then you have a problem with what's called dynamic range. In other words, if your instrumentation just can't go that high, if the signal is small. If instead you can have there be subtraction through optics instead of through electronics, you can get rid of that dynamic range issue. So again, this is trying to talk about some of the benefits of using lights and atoms. So at the heart of this atomic magnetometer or quantum magnetometer are alkali atoms. In this case, there's two atoms we use, which is rubidium and potassium. And you take light and you give it angular momentum. Use the quantum properties of light to give it angular momentum. The atoms absorb that light. They get the angular momentum. And so they get alignment. That high alignment, you get nearly 100% of the atoms to be aligned together. And that creates your sensor. Now, the signal that comes in, it tips those atoms out of alignment. And the probe laser reads it. I'm not getting into the physics here. Bill only gave me 10 minutes talk, so what can I say? So you have to talk to me about the physics, which is really cool physics, but I can't get into it too much. But we put on a tuning field. That's the field that creates the resonance. That's the basic idea of this atomic magnetometer, quantum magnetometer. Again, that tuning field is what gives you the tunability. So one of the places that could really use tunability is in the detection of explosives. They also have very nice quantum properties inside themselves that have intrinsic resonance frequencies. Again, very interesting physics, not enough time, but they exist. And so you see some TNT, it's like about a megahertz, some of the ones you may know. And Kyle Nixon recently, just last year, measured potassium chlorate, which is an IUV explosive. You guys might wonder, like, why am I allowed to detect explosives at Mason? You might be a little bit worried if you were a student here. In fact, I'm only allowed to detect explosives that you can buy at the hardware store. So the ones that I detect are the ones that are fertilizer explosives or can be used in firecrackers or something like that. I'm not allowed to have any TNT. Don't worry. There's no TNT in my lab. It's going to blow you up. So that tunability is nice because you could switch from one resonance frequency to another resonance frequency just by changing the current in a coil. So this is the coil. It's in my lab, designed by a student. In fact, these magnetometers that I'm using are from a collaborator. They're fiber coupled. That's how all these fibers are coming out. Those are the two frequencies that we want to go between. Darwin built this coil, so he recognized it. Here's two samples, potassium chloride and ammonium nitrate. And the reason why we want to use magnetometers, part of it is because when you do an excitation, you have to wait. So your thermodynamics tell you have to come back to that place. And ammonium nitrate, again, that fertilizer explosive, is awful because its time constant is about 16 seconds. That means I can take a measurement, I have to wait a half a minute, and I take another measurement. So that's very painful if you wanted to measure something rapidly. However, if I can measure ammonium nitrate, potassium chlorate, then another explosive, and I can use up all my wait time by measuring other things, I win by a lot. This was a demonstration of doing that, and we were successful at being able to do that interleave. It had some challenges to it, but Darwin, who is a dual electrical engineering and physics major, right? So that's what makes it very nice. Was able to make a dual frequency excitation coil. So he's showing that it resonates in two places. It's not a simple thing to build. And plus, we were able to do some fun little electrical stuff in which we take diodes. We kill off our excitation pulse really quickly. So some fun, again, electrical engineering piece of the project as well. So we had on top, we have this detection of ammonium nitrate and potassium chloride the conventional way. So coil, we did it serially. The reason why we don't do the interleave with the coil is because, in fact, you have to take out the tuning components one for another. It's terrible what you did to me. Okay, so anyway, this is the magnetometer signal. Ooh, pretty, anyway, very beautiful magnetometer signals. And not only did we gain that interleaving, we also gained where it is. So military people always like to know, well, where is the explosive? Not just, is it there? So the magnetometers have that going for them. So with my very, very small amount of time left to you, I just want to you can talk to Robert after it, is this idea of an intrinsic radiometer. That is, you put light through one cell, you put a half wave plate, you put the light in the other cell, and it optically subtracts. So if you had a gradient signal, that would add, but if you have a signal that's the same, it subtracts. And it does it before it ever reaches the sensor. So you can have a really large signal that you don't like, get rid of it, and keep your little itty bitty signal left alone. And so I don't have any time. Anyway, Robert will talk me through how that goes. This is just a demonstration of it. This is the signal plus interference. When you don't have the wave plate, introduce the wave plate, get rid of all your interference. You can see there's a factor of 40 between these, and you just have your signal. So it's a beautiful demonstration. Plus, he was able to get down to sub-femtotesla sensitivity, which is a big deal in our field, 10 to the minus 15 Tesla per root hertz. And so retains both of them. So in conclusion, quantum magnetometers, they're easy to tune to resonance. We demonstrated this interleave protection. They also have some really nice properties about this intrinsic radiometer, which gives a clean subtraction, which I just showed you the clean subtraction, plus the sensitivity. So those are the two things I was hoping to get across. This is Robert here, Darwin's there. Jafar is somewhere here too, but he gave a poster yesterday, so I didn't talk about his interesting work. And this is all done in collaboration with other people, other institutions.
Well, don't you know that next time really I have one question for Dr.
Yes, any material. It's just the military like to give us money for that particular material. But it can't, it has to be something that's has a crystal. Because it has to have an electric field gradient. So that's what the physics is of having to have it something that's sort of static. So liquid, no. Yeah, well, crystal just means solid. Yeah, C4, yes. Yeah.
That was a wonderful talk.
Thank you.
I made some fun.
Next speaker is Dr. Ghimire from Physics Department.
Thank you. Thank you. So my talk is about this synthesis approach to quantum materials. We have this awesome talk earlier by Professor McQueen about what are quantum materials, and most of the thing, he is also a scientific person. So we have probably some common here, the thing that we'll be talking about. So I'll kind of show you how by synthesis and some measurement technique, we are trying to find some quantum materials or quantum physics in materials. That's what I'll be kind of focusing to. Probably this definition is what Professor McQueen contributed to. I like them. There are many definitions to quantum materials, and one of the ways that quantum materials are defined, he also already mentioned, is that materials in which the extraordinary effects of quantum mechanics give rise to exotic and incredible properties. One of the things that he mentioned in this type was the superconductivity. I put the magnets here because magnets, as though we learned that ferromagnet may not be the quantum phenomenon, but there are certain magnets where the phases can play a role and can give rise to the quantum mechanical phenomena. And those are the things that we are studying, and I might show you a little bit of that effect too. So this is the approach that we do is, we put our hands dirty in the lab. We work with chemicals. We kind of put on these flames, blow tubes, and make reactions on those tubes. Primarily, we focus on two different methods. There are the kind of pictures of some of the crystals that are grown in my lab, and again, this paradigm is a very amazing source that even we can access that by applying proposals to. We're looking to that, yet we have not been in a situation that we needed. And then the thing is that after we synthesize materials, We have these crystals, right? Beautiful crystals. What do we do with those crystals? We need to do the measurement. We need to know what are the properties of that material, and then we need measurements. Basically, we do a lot of measurements in our lab with a physical property measurement system. We also make trips to if we need very large magnetic field, or if we need neutrons to extract some of the magnetic properties of the materials. Here is one of my graduate students here, and we talk later. Was doing some experiment a couple of months ago in a high magnetic field lab down in Tallahassee. He already made 2 trips last year, and then we use this facility in Los Alamos as well, where we can reach up to 6 factors of the pulse field. Then this Newton scattering is a technique where you can probe the ordered structure of the magnetism. It's the magnetic structure. And that's also something we do partly. Sometimes we collaborate with our collaborators. So now the thing is that what we are studying is something that I'll spend some time on. Is the first set of material is what we call the Ghimire magne. Professor McQueen, just a little bit about when he was talking about quantum spin liquid on this system. We're not studying quantum spin liquid, but we are studying some electronic properties and some also magnetic properties that can occur in these materials and the interplay between them. What happens is that when atoms are arranged in this pattern, which is called a Kang pattern, it can lead to the electronic structure, something like this, which has very, very steep dispersion bands. At the same time, it has this flat dispersion bands. These are 2 extreme limits of a band structure. They can occur in the same material. And it can manifest some of these quantum phenomena, both of these states, in a single material. That's one of the interests. Another interest, it can again introduce frustration if these atoms are magnetic atoms. They can give rise to interesting magnetic structures. And a single system that can provide interesting electronic structure as well as interesting magnetic structure. And we can study the interplay between these electronic and magnetic structure in this system. That's why we are studying it. And what we are studying is one of these compounds that we are studying, a set of compounds, is this RMN6SN6 compound, where this R is a rare earth element. The reason this system is very interesting is the way how these magnetic atoms are arranged. Manganese is one of the magnetic atoms. It makes these layers here different. These black atoms are these manganese, and these are the ones that are arranged in this Ghimire fashion. And what we can do is we can replace all these tin atoms with other elements. You will see 2 talks later on from my students where they are trying to replace these tins with germanium or gallium and then find different and tune different magnetic and electronic properties. And then we can even replace these green balls, which are these rare earth balls, with a different magnetic rare earth or non-magnetic rare earth, and that changes the property. Not only changes the electronic property, but also the magnetism into it. It's a very rich playground for these electronic and interplay between electronic and magnetic properties. And we collaborate a lot with Professor Martin in theory, and these are different my co-members who are working on different materials of this sample. Another one that we're working on is again these dichalcosanides. We saw some of the dichalcosanides earlier in previous 2 months, I'd say. And one of the systems that I kind of started working sometimes in 2018 timeframe was this cobalt intercalcate niobium disulfide. What happens is that this is one layer of this niobium disulfide. This is another layer of niobium disulfide. And these cobalt atoms are stuck in between these layers. When we stuck between these layers, it makes a different structure. And it can give rise to, again, very interesting properties to the system, very interesting magnetic properties, electronic properties. One of the things I discovered is this large all conductivity, which was not expected in this material, in this type of material. And was a very surprise to me. Now I think it's speaking some momentum on this type of material. So we collaborate with different groups, Professor Bora's group, Professor Gari's group, within this department, again Professor Maji and Resam and Hari and Peter are working on different sets of compounds on this system. Another one is what we are working on is called ultramagnets. This is a new form of magnetic material. And what it is we have these antiferromagnets where the spins are anti-aligned, ferromagnets where spins are both pointing in the same direction. But this is very new, recently discovered. The theory came like 2 to 3 years ago, and believe me, this discovery had some role into it because this is a collinear ferromagnet and it gives rise to large anomalous Hall effect. Exactly, and it was predicted to be one of the ultramagnets and turned out to be not because of its some delicate things. Then these ultramagnets are in between ferromagnet and antiferromagnet. They are actually antiferromagnet, but some of the properties become like ferromagnet, and these can be very helpful in terms of spin turning application. Again, I won't have time to go through all these things, but just give you a kind of feel about it. Then the next thing is this complicated, the diagram here. But what happens is that I mentioned you that magnetic structures can have these topological properties. When we have this kind of very complex ordering of magnetism, and when we pass electrons through these complex magnetic texture, these electrons, the phase of these electrons, can when they make this one complete rotation, the phase may not come to its original phase, and that is something called non-zero Berry phase, and it can give rise to some emergent properties. And that was what was realized in this compound magnetic suicide. And what that does is that when it has this manifestation in terms of Hall effect, which is called topological Hall effect in this material, the electrons then can kick force into these textures, and then they can move it much easier than it would have been in a regular magnet, for example, domain walls of ferromagnet. So this spin texture was soon to be moved by 10,000 times smaller current than we require to move these domain walls in ferromagnet, which is, by the way, is what is required in spin turning application. And then, we recently discovered some very similar feature, not exactly like that, but very similar feature. What we think is a dynamical fermion in one of these stages of a material that we are studying. It was a recent discovery, and we are trying to investigate similar effects. Our hypothesis is that it should behave similar way. We are now trying to experimentally observe, see whether we can find the same behavior in this kind of material. So that is one thing that we're interested in. First, testing this material and finding all the materials, that can have similar behavior is one of our goals. In summary, what we do is we focus on the fundamental science of, that potentially can impact the future electronic devices. And our research is on the study of electronic and magnetic properties or interplay between them. And then we do that by synthesizing materials and studying their properties. Here is awesome crystal that Curre grew. Thank you.
One question for Ghimire.
Oh, sure. So yeah, sure. Oh, it's not. It does not form into that structure, but because of temperature fluctuates there. And although you can observe its order of the state, what happens is that you can measure